Hey everyone, in this video I'm going to show you how we can use Euclidean distance to identify chart patterns in candlestick data. So here I have a CSV file which contains the hourly candlestick data for Bitcoin for the year 2024. So if you do the math, we have 365 days times 24 hours every day. So that comes around 8,700 bars. So we have the open, high, low, close and volume values for these candles, and we also have RSI values, which is what we're going to use to identify patterns. And the reason we're going to use RSI is because we need to normalize the data when identifying patterns. And the good thing about RSI is that the value is squished between 0 and 100, right? The smallest value the RSI column can have is 0, which indicates extremely overbought, and the highest value is 100. Sorry, the 0 indicates extremely oversold and 100 indicates extremely overbought. So because the values are already normalized between 0 and 100, that would be a good column to use to identify patterns. Alright, now let's understand how the Euclidean distance is calculated. Let's say the blue line is the pattern that you want to identify, and the red line is the pattern that you're comparing against to identify the Euclidean distance. Okay, so in this case we have a sample size of 8. So we're going to say the window size is 8, and we take for each point, we take the difference. So let's take the first one, right? The blue line is 40 and the red line is 70. So the difference is 30, right? So we take the difference and do a square. 30 square is 900. And then we go to the second point and repeat the same. So the blue line is 60 and the red line is 40. So the difference is 20. So 20 square is 400. And then we do the same for all these points, and if we do the same for the last point, the blue line is 50 and the red line is 30. So the difference is 20, again the square is 400. Then what we do is, we do a sum of all these squares and identify the square root of the sum. So the sum of squares is 5800 and the square root of 5800 is 76.15. So 76.15 is the Euclidean distance between these two patterns. So smaller the number, greater the similarity. And what we will do is, we'll take the entire historical data and calculate the Euclidean distance for all the possible patterns for the particular window size, and then we rank them based on the smallest value to get the closest pattern. So that's the approach we're going to use to identify chart patterns. So here is a quick and dirty project that I created to identify the patterns using Euclidean distance for this CSV file. So excuse the crude interface. I want to focus on emphasize on the functionality rather than the aesthetics. So I'll explain how this works. So first we have the window size. So the size of the window that we use to identify patterns, and you can select a value between 50 and 300, which I think covers all the possible patterns that you want to identify. And for now, let's just default the value to 100. And then we have step size. We'll talk about step size later. And then we have top n matches, which will display the top 10 patterns down below. And we'll also talk about start date time later. For now, let's just select a random pattern. So when you click random pattern, what this does is it selects a random pattern from this data for this window size 100, and then try to find the matching patterns for the selected pattern. All right, let's click random pattern, and now we'll see a lot of lines. So the blue line is the pattern that it selected, and all the gray lines are the patterns matching with this blue line in the historical data. Now this might seem a bit convoluted, so for now I'll just reduce the top n matches to 5 and rerun this again. So now we can see, you see less noise, so you can see the similarity. So you can see all the gray lines are very close to the blue line in terms of pattern, and you have a labels for these lines. So if you select, you can actually hide or make them visible by double clicking on these titles. So let's just enable one. Okay, so this is the closest one. It has a score of 78.23, and the selected pattern is on June 24th, 1:30 p.m. Keep in mind, this is hourly data, right? So every day we have 24 bars. So the closest it could find for this is on 24th of April, and it has a score of 78. All right, so you can see the gray line is very close to the blue line, indicating that it's a very close match. Let's look at the second line. Yeah, even the second line is very close. It has a slightly higher score of 85, and so on and so forth. As the score increases, the deviation also increases. So that is how you can use Euclidean distance to identify similarity in patterns. Now let's look at what step size is. So step size tells you the number of candles the window has to shift to go through while going through the historical data. So what do I mean by that? So if I set the step size to 1, what this does is if the window size is 100, then out of these 8000 bars, while it's doing the comparison, the first window will be from index 0 to index 99. And then the second window will be index 1 to index 100. That's because the step size is 1. So we increment the window by just one step while performing the matching analysis. Now, having the step size to 1 is computationally very expensive, because you have to run this pattern through all the 8000 or so bars in the data. So you're essentially running calculating distance for the entire history, which is very inefficient. And you'll also get a lot of false positives, because think about it. So if each window is only differentiated by just one bar, that means if a pattern is matching, then in the result you will find a lot of patterns which are adjacent to that window. Let me explain what I mean by that. So if we set the step size to 1, and if I run the random pattern, you can see this is the pattern and it's on May 24th, right? So if you look at the first one, this is identified on 14th of November, right? If you look at the second closest pattern, that is also on 14th of November. And the third one is also 14th of November. So again, you can see that these three windows are shifted slightly by 1 or 2 bars. That's it, not more than that. So these adjacent bars are not truly matched, right? Because if you look at it, you want the patterns to spread out in the data, right? You don't want adjacent patterns, because most likely you're just looking at a single pattern that is slightly shifted by a few bars. So to avoid that, you better increase the step size. And again, you can play around with different values. If I set the step size to 4, you can see it is still finding overlapping patterns, right? You can see on September 22nd and September 23rd. So what I found is step size of 10 has enough spacing between windows to identify distinct matches. Alright, now if I set the step size 1, you can see one pattern is found in April, the other one in December, one in October. So yeah, the windows are spread out, which is what you want. And then you have a start date time field, and this is useful because let's say you want the window, the base pattern that you want to find a match for, if you want that window to start from a particular time. So one thing I noticed is on November 1st, there is a bullish divergence kind of a pattern. So if I select that, again, the reason I know that is because I went to TradingView, I looked at the historical RSI patterns and found on September 1st or September 2nd, there is a bullish divergence pattern. Yeah, you can see there is a dip below 30, and then there is another dip here in the 30s, and there is a higher low on the RSI value, and there was a lower low on the price pattern. So that indicates a bullish divergence. So I wanted to see if we can identify bullish divergence patterns. So yeah, if you want the window to start at a particular point in time, you can select it with this date time field, and then you can find the matching patterns for that particular window. And one other thing to keep in mind is that you won't find exact pattern in most cases. Again, if there is an exactly matching pattern, you'll find it, but because we are dealing with candlestick data, it's more likely that this data is somewhat random, right? It's not data from a sensor, right? Because a sensor behaves in a specific way throughout its life cycle, and and the deviation from the behavior from its core behavior is less often. Let's just say that it's not too often. But that is not the case with candlestick data, right? Because candlestick data is more random, because candlestick data is essentially people just betting on price going up or down, likely to be random than a sensor data. Although this looks like a prudent approach to identify patterns because we are not looking at exact match, there are some drawbacks in using this approach. The first drawback is a fixed window size. So let's say the pattern that you're trying to find is of a specific window size, but the matching pattern can span across a higher window size, right? For example, you have a bullish divergence within a span of, let's say, 100 candles, but in reality this can happen across 150 bars. So you don't exactly know what the window size is before you run the matching pattern. So one technique I found to overcome this challenge is by having a flexible window size, and maybe when you're trying to build your own models, try to pre-calculate the Euclidean distance for all the different window sizes, and maybe increment each window size by 1, right? For example, in this case, right, we have 50 to 300. So maybe you can calculate all the Euclidean distances for 50, and then 60, 70, 80, and so on up till 300. So that way you have around 5 plus 10 and 10. Yeah, 25. You have 25 windows, the Euclidean distance calculated for 25 windows, and that gives you enough flexibility to find patterns with variable window size. The second issue is, let's say you have a window and you want to emphasize on a specific portion of the pattern, right? Let's say you want a portion of the pattern to take higher precedence over the rest of the pattern. Let's take this pattern, what we have on the screen. So you want to identify bullish divergence. Say you want to identify bullish divergence. Then you want this part of the chart of the pattern to take precedence over the rest of the pattern, right? That is difficult to achieve using this approach. So when you define a window, all the points are given equal precedence. Maybe one way to overcome that is by having weights. So you can allocate a higher weight for a portion of the pattern and maybe a smaller weight for the rest of the pattern. That should emphasize more on the pattern that you want to highlight. So this is another drawback of using Euclidean distance, that you cannot emphasize on a portion of the pattern. You can find the link to this project on my website dkhub.com. If you go to RSI Pattern Finder and hit type in, that will take you to this tool. And I also shared the code for this project on GitHub. I'll leave a link to this repository in the description box. That's it. You can use this tool to play around with the Finder. No need to download anything or install anything. You can download the project and replace the CSV file that is present in the index.js file, and replace it with your own CSV file and play with this toolkit. Make sure the data in the CSV file is in the same format as this one. That's it for this video. Before I wrap up, I want to mention that the things that I discussed in this video can also be achieved using a vector database. In fact, I would say that this video is a precursor to a video that I'm going to do very soon on how we can use a vector database to identify similarity in patterns. Now, you must have heard this term vector database quite a bit in the recent past, but in most cases, I've seen people using vector database to do a semantic search, right? And they act as a memory for large language models. But many don't know that you can use a vector database to also conduct similarity search. But if I had done this video using a database, then you wouldn't understand what's really going on under the hood. So I wanted to do a bare bones version of this toolkit, so you understand exactly what's going on at each and every step before we can simplify this using a vector database. So more on that in the very near future. And as always, leave your suggestions and feedback in the comment section, and I will talk to you in the next one. Bye.